So I will give you a quick overlook just to be on the same page about what Pregel and Giraph is, just 3 or 4 slides so that you can appreciate our work on Lighthouse, which builds on top of the Pregel system, the Pregel model I should say. So first, as I said, like a bunch of slides. Giraph is a open source implementation in the Hadoop ecosystem of a system called Pregel from Google, published in 2010. It was like Hadoop developed by Yahoo and donated to the Apache Software Foundation in 2011. It was promoted top-level project, and now is actively developed and used at Facebook mostly and LinkedIn, Yahoo. And we have contributions from companies like Spotify, eBay, and so on and so forth. So it's in the business of heavy lifting with respect to graph processing and most importantly and precisely analytics. So Giraph is not a graph database to start with, like Peter pointed out before. So it all builds around this so-called vertex-centric API that Pregel introduced. Many systems are heavily inspired if they don't necessarily actually implement the system, the model itself. So you are on the same page. It's a computation divided in a number of super steps, so-called super steps. So you can basically design your graph algorithms as iterative algorithms. And vertices, the data model is have a graph with the values associated to a vertex, and also to edges, for example, to map weights. And these vertices are executed at least a maximum once per super step, and they can update the values associated to the vertex according to the messages it has received, and the vertex can send messages around. So basically, it's an iterative computation where messages are sent around messages and update their local value based on the message that they have received. Because it's asynchronous, all the messages produced at super step I are delivered at that time but processed at the following super step, right? So, and this is very simple, completely local-based computation. So vertices access only their local information, which makes it extremely, to a certain extent, parallelizable. Underneath, there is the very famous BSP model. So our vertices, the vertices loaded in memory, are divided by hash partitioning across different processing units. And and basically the messages produced by the vertices are the messages produced by the processing units in the BSP model. So the model is basically, the mapping between Pregel and the BSP is 1-to-1. Giraph is built, it is a first citizen of the Hadoop ecosystem. So it runs and reads data from any store in the Hadoop ecosystem. It runs either as a MapReduce job if you don't have Yarn. If you have Yarn, it will run as within its containers. So it runs as an application in Hadoop. And it's a master worker architecture. So you have a worker that you have workers that have vertices in memory, compute functions on vertices, and exchange directly between each other the messages, and the worker and the master just orchestrates this series of computations. So this is all there is to know about the Pregel model that we use and we borrow. So the idea is cool. Giraph and Pregel allows you, just like MapReduce, to write very simple user-defined functions. No explicit synchronization, no explicit parallelization. You just write a single function in Java, and this is automatically parallelized for you. However, as cool as it may sound, a lot of people don't like writing Java code, even if it's so simple, because in particular for complex algorithms such as pattern matching, every time you want to find a different shape of your pattern means you have to write extensive, potentially error-prone Java code, right? So imagine you have to, you're prototyping and you just have to switch this and that, and actually don't need to explain this to database people. It's much more likely that is you will insert bugs, or it's actually just faster to be able to express your patterns through high-level language and then have the tool process it for you optimally. So this is obviously a concept that we are borrowing and trying to see the Giraph as a possible runtime to execute graph pattern matching. So we follow the typical approach where we are actually borrowing the Cypher query language from the Neo4j people as a way of nicely express our graph patterns. We extract a query graph out of a Cypher query, and we compute a query plan based on this, a cost model and some statistics that we're developing. And this query plan that is based on let's say Giraph-based or vertex-centric-based algebra is executed as Giraph computation purely on the Hadoop cluster. So I'm going to explain you what this Giraph execution algebra is all about that is a little bit what is the nice part of this game, I believe. So the game is, okay, we have vertices that are there in memory, and they're sending messages to other vertices, which are in other machines, which pretty much sounds like a hash joint in my head. So what about we have these patterns, these bindings, and we keep in memory a big binding table with all the instances of our bindings, right? And this binding table we distribute across all our workers, and more precisely across all the vertices that are potential matches for these bindings, right? So our binding table is partitioned across all the workers, and more precisely, more fine-grainedly across all the vertices that will process these bindings, these instances, by means of local information. So our operators are all executed per vertex, and all receive as an input the current binding table. They produce a new output binding table that is sent around through messages, right? This is the basic concept. So we have a bunch of these operators. One is a typical scan. It goes through all the vertices, matching for a particular set of properties or classes for the vertices, and starts a traversal for a graph pattern matching. Then we have a select, which selects some of these properties, for example, and prunes entries in the binding table. We can put on the binding tables not only the vertex it is, but additional information, because as I will show in a moment, we are supporting the property graph data model. And then you have a bunch of two types of joins that we model directly to the message-based paradigm. I'm going to show an example. Anyway, before we get into the details of each of these operators that we can discuss offline, I'll show you a quick overview of how this works. So like I said, our binding table is partitioned and sent around in messages and processed by vertices. So imagine that we have a toy example query like this in Cypher. This is just a toy query. We want to find all the people, for example, on LDBC, whose first name is Antonio. They work at a company that is located in a certain country, and these people have to have a browser. That is Chrome, right? So like you can see, we have properties associated to vertices or relationships. Relationships have labels. Vertices have also labels, multiple ones potentially. So a person can be a person, can be an employee, and so on and so forth. And edges have also potentially key value pairs properties, right? So out of this particular specific query, we can compute with our algebra two different plans. So a lefty plan and a bushy plan, and it is up to the cost model, to the planner, to find which one should be the correct one, or the most efficient one, I should say. Right, so this is still a pretty database standard. This is an example of a data graph, right? So we have two companies, which are the middle vertices with, they belong to, that's why they have this company label. And we have 8 people. These 8 people have a bunch of properties: their first name, their birth date, and they are connected to this company through a works at relationship, right? So now imagine that the query is super simple. And we want to find all the people that are people, and they work at a specific company. And we want to know the birth date of these people and the ID, their ID and the ID of the company. Well, it's pretty useless, but it helps us go through the example. So what happens is, the first thing, what the plan will do is we'll scan all the vertices in memory into these into these hash maps that are in each workers, which is what the Pregos model does at each superstep. It will only select the people who have the person label, and then it will project the birth date property on the binding table, and then compute a step join through the work at relationship, which is exactly what I'm showing here. What you see on the left, you have the vertices, and the binding table contains at the beginning only the IDs, which is due to the fact that it's a person. Right after the scan, in the same superstep, each vertex is also adding to its row, to the specific row in its binding table, in the corresponding row in the binding table. Also, it's in the second column, also its property as a birth date. And it executes also in the same superstep the so-called step join, where it adds the ID of the other end, so the endpoint of the edge, the works at relationship, and sends this message to the other end, so basically to the company vertices, right? And the next superstep, this message will be received, and well, actually the plan is over, so that those vertices can can actually write this distributed table to HDFS. imagining that it was more selective. These companies, imagine you wanted a company that is based in the US and the location is a property, that these company vertices would select, would prune the rows that don't belong to what they don't belong to by not being a vertex, a company in the US, right? So this is the hash join works similarly, but this is the idea of how we can do this by instrumenting, let's say, vertex-based, vertex-centric APIs. So this is still a fairly simple exercise to a certain extent for systems like yours, I should say. What is more interesting when you start looking at a system like Giraph is it's a big monster, so you want it to do some heavy lifting, and more importantly, you want to exploit its ability to do iterative computations quickly. One of the things that we think is the case is reachability, connectivity queries, such as shortest paths. We believe that we can leverage the Giraph and the Prego model with respect to this particular task. That's why we are extending, and Peter Junior, we call it in the back, is working on this, so you can talk to him if you want the details. The idea is we want to extend the Cypher language to make path queries and shortest path queries first citizens of the language. Right now in Cypher, you have some kind of black box approach where you can express a start and an end node with a variable length path, but you don't have very much control either on the cost function, so what is the weight, what is the shortest path, how you compute the shortest path, and more importantly, you cannot really select. You can basically just define one relationship that is going to be followed by the shortest path, and you don't have more control into specifying more restrictions either on vertex properties or edge properties and so on and so forth. Also, it doesn't support a top n for each pair, shortest path, and so on and so forth. So we have a proposal for this operator. It is the following. So first of all, the first thing to notice is you can put in the edge. So this is an edge, which can represent easily very nicely by an arrow. You can start inserting all your restrictions in the part of the edge expression that allows you to put your label. So what it means is that you want to go through from each vertex to any other through a number of relationships and you will traverse an edge as long as this edge as an endpoint or target vertex doesn't have a property true for danger. So it's not a dangerous path, right? And you can actually put more of these properties, conjunct them or disjunct them. The second thing to notice here is that we introduce the most important part is you express the cheapest, if you want the cheapest of the shortest path. In this case, it's the n of top n. So we want the three cheapest one, and cost function is the distance and the speed that you can traverse that road, and you can also request the cost of the shortest path to be bound to the length variable, and return all of this. This should be all there is to know about this extension. We can discuss, this is a work in progress, we can discuss what do you think is more reasonable and useful for such an extension. And we have an Giraph implementation for this particular operator. If you know a little bit about the Prego model, you know that one of the things you don't want to do is all pair shortest paths on Prego, and that's why we are doing it. So it's very tough. I think it's very interesting. The current solution is computing the shortest path from many to many in two steps. First, it computes some kind of routing of the paths, and the second phase, it exploits this routing to actually build the paths themselves. And on the social networking side of the LDBC data set, we have tested this operator to find some shortest path between people. I don't remember what the weight was used. What did you use as a weight, Peter?
It was depending on the time the people use.
Right, so the length of the relationship was the weight, and we're trying to compute these all very shortest paths, and this is the scalability figures for these preliminary results. And yes, this brings me to the end of this talk. If you have any questions.
Thanks for the results of the benchmark. I'm interested, is there some some comparison to another graph database in your?
No, so
evaluation?
there is not yet any comparison. So what I've just described is preliminary prototype we have. So it runs, it produces correct results so far, but we're working on its scalability. So we have been able to. We are still working on fine-tuning it before we want to test against, for example, Neo4j. So I don't have those numbers yet. Okay, thank you.
Okay, thanks, Claudio.